Welcome to our talk. I'm Daniel, this is Felix. We are workmates from Deutsche Bahn. This is Germany's largest railway operator, and in particular we're working at DB Systel. This is the bunch of computer scientists, software engineers and data scientists at Deutsche Bahn. And we are working to improve the quality of Deutsche Bahn services. So our customers are, for example, those that run these fancy high-speed trains, but also station operators which operate like escalators. We also have energy generating facilities, and all this equipment tends to fail at some point. That's clear. Also, at some point, it gets repaired. That's also clear. But we try to improve the MTTR, so the mean time to repair, by providing software assistance to service personnel. So for like 2 years ago, we are working now on a universal platform in order to provide condition monitoring as a prerequisite for predictive maintenance, and we want to build it in a universal way, and therefore we are listening into machinery. And we stick sensors like these microphones into machines in order to detect their state and alarm personnel in case something seems to break. The challenges here, probably most of you know them, as it is often the case in data science, is that we want to have generalizing models. Also, we are not in a research facility, but in industry. Therefore, our customers expect improvements pretty early on, even in situations with little data and maybe poorly annotated data. We've been choosing a machine learning approach actually to address that, and we tackle these challenges using a transfer learning approach. So in a nutshell again, condition monitoring goals: we want to decrease the maintenance costs, optimize the personal placement since service personnel cannot be everywhere all the time, and we want to increase the availability since some of our customers have to provide such an availability of machinery in order to allow operations. Transfer learning goals, in our sense, are to increase the prediction accuracy and also to allow a quick start with the customer. Let's have a look at the system architecture that we have established over time here for the service delivery. So as I pointed out, we put plenty of these microphones into the field. So we have sensor boxes developed using Raspberry Pis in a, let's say, robust variant using embedded microtechnology integrated boards. We are using the Eclipse Foundation software stack, which is also used in IoT scenarios, Cura, for example, and we use these to sample actually the audio emissions from the machinery and compress it, transfer it back to the cloud backend, where we are using plenty of Linux, using Amazon Web Services in that case, and we are managing our fleet using Command Build and Chef, and look into the data using Grafana, the TIC stack, and also the ELK stack. And we make extensive use of the Python language, Java, Ruby, and also MQTT messaging. On the data analysis pipeline part, actually we do predictions in the field, also in the Cura framework. We train our models actually in the backend on the cloud side using TensorFlow and Keras. And yeah, we also use a couple of more technologies which might be pretty familiar to you. Let's go into particular matters now. So for 2 years now, we are recording data from escalators, and Deutsche Bahn operates about 1,000 of them in Germany. And yeah, failures in such escalators tend to become very costly pretty soon if you do not stop the machinery in time, since yeah, they wear off very quickly. And also it is important for maintenance personnel to schedule maintenance on these escalators in the night shift in order not to conflict with the accessibility contractual liabilities here. And yeah, I can show you a couple of issues with these escalators. So mostly it is about foreign bodies which get somehow into the machines, like coins, glass, crushed gravel and stuff like that, screws that fell off luggages, and yeah, then they somehow wear off the machine, and we want to detect that early on. Here I brought some sound examples from an escalator in Hamburg. The top plot is the waveform, and we transform actually the waveform into spectrograms. So we consider also the frequency and the time space in order to detect the machine's health state, so to say. So this is a good case here. Maybe you focus on the lower part on the spectrogram. Now I'm switching to a squeaky to a squeaky recording. So here the steps are not properly adjusted, and yeah, they make a very intensive noise, and also the ball bearings are actually suffering and tend to fail after some time if no maintenance personnel is about to fix that. So you can see here that there's plenty of power, in these recordings on different frequencies. You can see that it has a certain periodicity, since the machine is running at constant speed, and the steps are passing by the microphone at a constant rate. And yeah, basically, as we've seen in the previous talk, we have seen that convolutional neural networks are very good to detect patterns in pictures, and we are using such spectrograms actually as input data to our detection schemes, and Felix is about to present these detection schemes to you.
Yeah, thanks Daniel, and hi also from my side. So I want to give you an overview of what we've been doing in the past. So as he already mentioned, we use convolutional neural networks and use the spectrograms as input images. And we then find out what kind of state the machine is in at any given moment in time. And we have, of course, the problem that if you know what the sound is right now, it might not be that it's the sound the machine is doing all the time. So after this, we need to do some kind of post-processing to get out some kind of oscillation in our predictions. So as Daniel mentioned, if we have a new use case, we might have really little data. So how could we use transfer learning to do something about that and reduce the time and cost for data labeling and acquisition of new audio? And this approach we've been using before. So we had this escalator sound data set where we could go to an escalator and basically put it in any state we want. So we threw in gravel, or we hit every part in the machine with hammers and stuff. So we have this data set. Then we train our models, and we get a condition monitoring classifier. And a problem we have there is also, let's say we find out, okay, there's a new failure state, and we don't have the data for it yet. Maybe we only have a few samples, and that's also a use case we want to use transfer learning for. And here I give you an overview of how we are using transfer learning. So actually, if you look in the scenario of transfer learning in vision, it's quite often that there are huge pre-trained networks available which have been trained on many millions of images. It's not the same case in audio. There's one huge data set, it's called audio set. I think it has 22 million snippets from YouTube. But the research is just getting started there, basically. There are a few good results already, but we decided to transfer knowledge from the computer vision models and use that because if you know in these early layers, the models tend to learn, let's say, edges, borders, and if we cut off our model, as is kind of depicted here, and see the activations, we use what has been already done in the vision department. And what we decided is to not refit some new neural networks layers, but instead use more traditional approaches like support vector machines, random forest classifiers to fit new models on those activations. Back to the escalator case. So how does our experiment look like? We took a huge model pre-trained on ImageNet and applied basically the same approach I showed you right now. We wanted to compare different architectures, so we took Inception v3 model, VGG16, a couple of others, and then we fed our data set in and remembered the activations to train some random forests. And to make a comparison, we also took our approach we had before to train the neural networks from scratch, and let's see how that went. So in this case, we can see that on the x-axis you have the available audio training data in minutes. So we always increase the training data, then fit new models from the different approaches, and checked what kind of accuracy on our test set we could achieve. And of course, 18 minutes of audio is like really little, and we wouldn't probably give the recommendation, let's say, to our product owner to deploy such a model. But we can definitely see that there's a certain range in which these in blue and orange, the transfer learning approaches can reach a higher accuracy than would be possible when training a network from scratch. About this slide, we need to see it not so much quantitatively, maybe a little bit more qualitative, because to get these insights, we trained a huge number of models, and it took a really long time, so we couldn't do hyperparameter tuning for all the models. So if in doubt, it could always be the case that maybe optimized model, let's say from the training from scratch approach, could be getting a bigger accuracy. But what we say is, if we are in this box with the dotted lines, we can definitely say at least looking into the transfer learning approach is probably a good idea. And if we have less audio, then let's say to the left side of the red line, it would be advisable to consider deploying this approach. So what do we conclude from that? From a customer perspective, if we have little data, maybe only half an hour it could already be enough to at least give a reasonably good model to the customer and satisfy this need to get a result really quickly. And from a business perspective, we don't need expert time so much to give us the labeled data. We can already, with a little bit of help from the service technicians, get quite okay models. And technically, definitely in small data sets, we can get improved accuracy as compared to before. And what's also good about this approach, if we only take the activations and train a different model, we can choose a model which doesn't tend to overfit that much. And limitations, this is like one use case and it worked really well. If we would have a different use case and maybe different type of audio noises from the machines, it might be not so suitable there. But it's definitely a good thing to have in our toolbox, and the next time we have a new use case, we can think about deploying such a model. So where does that leave us? Next steps. We would like to deploy this and see how it compares to the models we have so far and get more insights how this approach can help us and maybe improve on it. Another thing that would be really nice, as I mentioned, we use models which were trained on image data, and we would like to utilize a huge data set that's built totally on machine sounds to do transfer learning in the future. And that's a topic we want to research, and we're working on building up this data, but at the moment, unfortunately, we're not there yet. But it's definitely on our agenda for 2019 and beyond. We would also like to see how suitable is this approach for deployment on our edge devices, and that's something we're, I would say, maybe close to testing out. And yeah, exactly. So that's it from our side. Thanks for the attention, and yeah, feel free to ask questions. So to repeat the question, why did we use convolutional neural networks? He mentioned audio data is sequential, why not use recurrent neural networks? So there has been work on that in acoustic scene classification and audio event detection. And what they found out is that you need less data usually to get quite good results if you use CNNs on time frequency representations, such as the spectrograms we use. There have been end-to-end approaches, but I think you need more data, and it's like a common approach to choose in that setting. To repeat the question, if we have tried something with Kalman filters, or if we have applied general GANs to augment our data maybe. We're talking about GANs, and it's something we would like to try out. And in audio classification, it's something that's been gaining popularity. We haven't done it yet, but Kalman filters I haven't thought about in the context yet.
We are looking for internships in Frankfurt, so if you're interested in GANs, just drop us a note.
To repeat the question, he's asking if we are thinking about open sourcing our data set.
Yes, okay. So we are making extensive use of open source software, as you have seen in the talk. Currently, our organization is paving the way actually to contribute back, because there are many hurdles, organizational and jurisdictional, and we are looking forward to that maybe next year. Yeah.
Okay, to repeat the question, how much time does it take to predict our model? We have deployed this kind of model on Raspberry Pis, and it can run in near real time, I would say. Okay.
First, business-wise, I guess you have like a maximum time to predict, otherwise it's not useful. And then I guess your model is able to predict the minimum time, so it is this range.
Yeah, so there's like a short-term component. So we have small recordings of several seconds, let's say 10 seconds, and but then we consider it a hyperparameter also, how to cut the spectrograms and cut them into patches, and then you can average over those. And depending on what kind of scenario you have, then you will have more or less noisy predictions, and then you can aggregate over that and apply some kind of statistics, maybe windowing what's coming in, and yeah, so of course it depends on what kind of machine you try to predict the condition. For some it might be important to act really quickly, for others you might have something that's more long term, where you can say, okay, let's see the average predictions in the last couple of hours or something. I hope that answers your question. Okay.
My question is about the network that you use. So my understanding is you don't really use any layers of inception or whatever. Or am I correct? And have you tried to also tune some layers of it, or what is the result?
So the question was whether we fine-tune those models when doing transfer learning, or whether we just take them as is and just see what the activations are. And in the experiment we showed in this talk, it was just taking activations as is. We have tried also some experiments where we do fine-tuning, but especially with that little data, we just didn't have the same results, and especially the kind of simplicity of doing it this way and getting a good result was something why we wanted to pursue that further, but maybe that's something for the future to take up again.
Yes. So we are aiming at a. Yes. Okay. So why the question was why we are using actually acoustic data, and if it can be put on rolling stock, right? Was it right? Yeah. Okay. So we are aiming at a universal platform which can be fit into various machineries, and also there's plenty of regulations in terms of modifying machinery. So this is non-intrusive. We just pick up the acoustic emissions. We do not have to change machinery itself. Okay. So this is the one part. We are also looking into rolling stock. Next week we're installing in trains in I think in Cottbus, and try to understand when steps which come out automatically from the train, when these tend to fail, because this is a big pain for this train operator actually. So rolling stock, yes. Acoustic emissions in terms of minimum or non-intrusiveness. Also, we haven't mentioned this today, we are looking also in acceleration data. And so this is minimal intrusive, since we can just glue the sensors on top of the machinery, and this is borderline in that sense. Yeah. Okay.
How do you think we use classification, and how often will you train the model with the new levels?
So to repeat the question, if I understood correctly, is it how often do we make a retraining on the models when basically in production? It depends. If you have like a data flow coming back in a use case, let's say, experts that can provide more labeled data, then there will be some retraining probably if it helps improve the model. We are currently working on some kind of continuous learning platform. We haven't fully implemented anything yet, but it's definitely something we want to take up in the future.
Also, in that case, we had the possibility to actually inject hardware faults into the escalator. So we are training a classification scheme. On the other hand, like for the power generation utilities, we won't be able to actually inject faults. Therefore, we are going to a trend detection scheme. We are currently working on autoencoders and spectral analysis to do that. And here we have to train way more often to find out these trend developments. Yeah. So it actually depends if we are going supervised or unsupervised. Yeah.